In this video, I continue the discussion of the numerical solution of ODEs by using the pendulum oscillation. The video is based on the example script example pendulum. The pendulum equation is given in line 8. It reads y double prime plus d times y prime plus g over l times sine of y equals 0. Because of the sine function, this equation is a nonlinear ODE. Y of t is the deviation of the pendulum from the vertical, measured in radians. D is a damping constant, which can be 0, in which case the pendulum is undamped. L is the length of the pendulum, G is a gravitational acceleration, and we can run the script with various values of D. So let's enter 0 for an undamped pendulum. Now we need to define the function handles, just as in the previous videos, the function handles that are passed to the solver as the first argument. The function handle for the pendulum is very similar to the one of the corresponding harmonic oscillator. The only difference is that in line 15 we have sine of y, in line 16 we have just y. This will allow us to give a comparison between the pendulum equation and the corresponding harmonic oscillation. I have defined a set of initial conditions. The first initial condition, which is pi over 12 in line 18, is the initial deviation of the pendulum from the vertical. And the second one, which is 0 in line 18, is the initial velocity of the pendulum. The velocity can be positive or negative. If it's positive, the velocity vector points counterclockwise. If it's negative, the velocity vector points clockwise. We can now run through this set of initial conditions, and I will also show you a graphical animated representation of the pendulum oscillation. So let's go to line 30. We select the first set of initial conditions. We set the title for the following plots. The t-span, the time span for the animation is 4 seconds from t equals 0 to t equals 4. I set a maximum step size of 0.008 and I solve the pendulum equation using the solver OD23. Now we can show the animated pendulum oscillations. You see the initial conditions in the title of this plot. The initial deviation is pi over 12, which is 15 degrees, and the initial velocity is 0. Which means we keep the pendulum at the initial position and then just let go. Okay, now I compute the solution over a time span from 0 to 15. And in this plot, we see both the pendulum angle and velocity, the blue lines, and the corresponding harmonic angle and velocity, the red lines, where the full line is the angle, the deviation, and the dotted line is the velocity. You see that for small initial deviation, pi over 12, 15 degrees, the two oscillations are nearly identical. The pendulum oscillation is just a little bit slower. Okay, let's pass to the next set of initial conditions. We have now 30 degrees of initial deviation. Initial velocity is still 0. Here we see again the angle and the velocity both for the pendulum and the harmonic oscillator. There is now a slightly larger difference between the pendulum and the harmonic oscillator. Let's go on. Now the initial velocity is 3, so the pendulum moves counterclockwise from its initial position. Again, we see a larger difference between the pendulum and the harmonic oscillator. Next, we see initial deviation of 30 degrees and the initial velocity of -3, so pointing clockwise. Next, the pendulum starts a deviation of 90 degrees. Initial velocity equals 0. Since there is no damping, it moves strictly from 90 degrees to -90 degrees. Now the initial velocity is -3. Again, we can compare the pendulum and the harmonic oscillation. They are now very much different. Now the initial velocity is -6, and now the pendulum goes round and round. And it will continue going round and round as there is no damping. Now the initial position is at 160 degrees. And we see that the pendulum equation is now very much different from the harmonic oscillation. It's much, much slower, and also the shape is quite different. Okay, this terminates the script. We can now try the same with a non-zero damping. So let's restart the script and set D to a value which is larger than 0. I encourage you to try different values of D on your own. Let's try 0.25 for this run. I just let the script run without any comments. And due to the damping now, the pendulum goes around only once. We can also see this in the trajectory. So this ends the discussion of the pendulum oscillation without and with damping.